Well, I was going to give you guys nerds, but I see my children have eaten too many of them to make it fair. And it seems wrong to only give 11 of you nerds. How can we decide who gets the nerds?
I think you should randomly throw them out and see if, like, we just fight with it. But you can, like, talk to them.
You guys don't have the love. You guys don't have the love.
Oh, what?
Fine, for the effort. I will go buy more, don't worry. I will somehow keep them away from my children. I tell you, Isaac could eat his weight in candy if I let him every day. I don't know, these pictures are, some people like these pictures to remember the chain rule. I personally think that you don't really need them. Like if you start to see the pattern, you know what the chain rule is. I mean, I don't know. I personally do not need these pictures. If they help you, great. If they don't, ignore them. If you read my notes, I have every single chain rule that you'll ever need in Calculus 3. All right? And there's like 30 examples in here. So, I don't know what I should cover in class. I'd actually rather spend more time back on the question of geometry, because I think that's harder for you guys to understand. So I'm going to do that. Okay, so again, you have these three ways to describe a surface. Level surface, parametrized surface, and a graph. Now, here's a picture of the idea. Oh wait, stupid scrolling. So in each case, what I want to do is, I mean, there's different tangent spaces at different points, right? Like there's not just one tangent space to a surface. At each point on the surface, you can imagine the tangent space, right? And so it's a local problem. There's like, you know, you say find the tangent space to a surface. You could just say like, what are you talking about? Which point, right? I have to tell you which point. Otherwise, it's not a reasonable request. And anyway, so here's a couple pictures of surfaces, and what I have here, and this is my brother made this, is a picture of a parametrized surface. The idea here is these grid of lines. Those are actually the coordinate curves. Those are what you get from either fixing u or fixing v. Really, the way to think of a parametric surface is, in some sense, you're taking the uv parameter space and you're gluing it on top of this curved space, and so they're kind of curved coordinate lines in some sense. So anyway, with respect to those, you can find the u-coordinate velocities and the v-coordinate velocities. You take the cross product of those, you get the normal vector field in the parametric sense. And then you see the hair? So there's like a picture of the normal vector field. It's always sticking perpendicular to the surface at each point. This one's more boring because the normal vector field to a plane is constant, right? Yes, as you guys saw on the next sheet, I have a torus. But as you can see, the normal vector field's always sticking out of the torus, right? That's the idea. And so this partial r, partial u, partial r, partial v cross product is actually what you need to do to calculate specifically the formula for these things. Given the parameterization, that's how you calculate it. But if you're like me, then the question remains, you've got these three different viewpoints, how are they connected, right? How are they connected? And so what I do in the notes here is I try to connect the viewpoints, right? So I'm gonna come back to this some other day. I don't think I want to try to rush through this in the 10 minutes we have. Let's look at let's go back and look at another, oh, I know what I want to do. I'm sorry, guys. Sorry, business calculus wore me out today a little bit. I really should tell you more about how to do partial derivatives. Fine. All right, so a harder example. So uxx plus uyy equals to 0 is known as Laplace's equation. So here's a hard question of chain rule. Convert Laplace's equation to polar coordinates. What is Laplace's equation in polar coordinates? I'll tell you what it's not. It's nothing to sneeze at, yes. It is not sorry, that was awful. It is not this. I mean, I wish it was just that. No, actually I don't. If it was just this, then life would be boring. It's not that. In fact, Laplace's equation in polar coordinates is really different. So the question then is, if we look at the partial derivative with respect to x of u, which is a function of r and, of u, which is a function of x, which is itself a function oh, I'm sorry. Let me try that again. Partial r of u, which is a function of r cosine theta, r sine theta. So I'm basically saying x is equal to r cosine theta, y is equal to r sine theta, and I want to calculate the partial derivative with respect to r of u rewritten in terms of polar coordinates. So what's the chain rule say? What's chain rule say here? So it says we do what? We do partial u, partial x, right? And then partial x, partial r, plus partial u, partial y, partial r, right? What is partial x, partial r? So you got yourself a cosine theta, ux, plus what? Plus sine theta uy. Now what happens when you calculate partial theta of u? Again, chain rule, right? Now, partial x, partial theta is minus r sine theta, right? And then I get plus r cosine theta uy. So, this is partial u, partial r. This is partial u, partial theta. Now, from these, you can extract relations in terms of, you can rewrite the derivative operators, one in terms of the other. So, like from this equation, let me call this star, let me call this equation star, star. If you remove the u's, you have the following partial operator equations. You have partial r is equal to cosine theta partial x plus sine theta partial y. And you have that partial theta is equal to minus r sine theta partial x plus r cosine theta partial partial y. Now what I want is I want to solve these equations for x and y. Can you guys see how to do that? So I want to take this and I want to solve for partial partial x and partial partial y. Let me show you how I do it. So what I have really is I have a matrix. My matrix is cosine theta, sine theta, and then minus r sine theta. Is there a question? I keep hearing talking. R cosine theta, and let's see here, partial partial x, partial partial y, and that's equal to partial r, and partial partial theta. So if I want to solve this, you could use Kramer's rule, you could use multiplication by inverse. I mean, whatever floats your boat. Tell you what, I'll use Kramer's rule. Kramer's rule says that partial partial x should be equal to the determinant of, let's see here, partial partial r, partial partial theta. I don't want to use Kramer's rule. I take it back. I'm going to use multiplication by inverse. I can't make up my mind. What's the inverse to this matrix? If you have a matrix A, B, C, D, the inverse to that is 1 over AD minus BC. You flip the diagonals, and you put minuses on the off diagonal. That's the rule. You need to learn this at some point. Why not learn it now? So the inverse to that matrix is what? So I get r cosine squared plus r sine squared, so I get 1 over r for this factor out front. And then I flip the diagonals, r cosine theta. I put minuses on the off diagonal, minus sine theta, and then r sine theta. And then I've got myself a cosine theta here. So there you go. That's the inverse matrix. So partial partial x, partial partial y is equal to 1 over r times that matrix. Okay, so what that gives me is this multiplies through to give me cosine theta partial partial r minus sine theta partial partial theta, and then I get sine theta partial partial r. I have a 1 over r here, plus cosine theta over r partial partial theta. In other words, the answer to the algebra question I posed over here is partial partial x is in fact cosine theta partial partial r and minus sine theta over r partial partial theta. And then partial partial y is sine theta partial partial r plus cosine theta over r partial partial theta. So as you can see, this is how you can rewrite the derivative with respect to x or the derivative with respect to y in terms of the polar coordinate derivatives. So how do you find Laplace's equation in polar coordinates? You do partial partial x of u, in the sense that that's equal to cosine theta partial partial r minus sine theta over r partial partial theta, and that again. I want to show you the answer. Give me a second. Can you search? Oh, there it is. So, come on, scroll for me, silly thing. So I just motivated for you why partial partial x is this expression, and likewise for partial partial y. You then you just have to do them twice, acting on the function. I used phi instead of u. It's the same thing though. It is not at all obvious why doing this brings you to here. There's like a half a page of calculation between here and here, which I invite you to try. It's a good exercise. It really is. I'm not joking. It's something you should be able to do. But it turns out that Laplace's equation ends up being this. So you have the term you expect, the term you don't quite expect, but it kind of makes sense. You just have 1 over r squared because you've got a theta squared, so dimensional analysis suggests that should be there. But then this is kind of surprising. There's this middle term. So this is a less trivial application of the chain rule for you. Anyway, have a good weekend. See you Monday with your questions. Tuesday, the homework will be due. Thanks. I mean, you could start working on the homework now. You don't have to wait till Monday.